So I am Benjamin, and I want to tell you something about how obfuscation can work on small embedded devices, because usually if you're talking about obfuscation, you're mostly thinking about desktop systems or maybe even your smartphone, but I want to explain a bit how it can work on embedded devices. And first of all, this is going to be a long talk, so first of all we are going to look at what obfuscation actually is and why you might want to use it. Then I'm going to give a quick demo of how reverse engineering can work on embedded devices, just so you know roughly what we are trying to prevent and the methods that can be used to reverse engineer. And then I'm going to talk a bit about analysis methods, and then I'm going to talk about the obfuscation itself. This is going to start with a rough overview, what's there available, and then I'm going to talk about desktop approaches and also explain why they might not be applicable to small embedded devices. Then of course we move to the embedded world, and this is going to conclude the presentation. And in the end, I guess we will have some time for questions, and we can also talk like today at the dinner. So of course, what is obfuscation? If you look at Wikipedia, in software development, obfuscation is a deliberate act of creating source or meshing code that is difficult for humans to understand in order to conceal its purpose, which can be used for security through obscurity, or its logic or implicit values embedded in it, primarily in order to prevent tampering or deter reverse engineering. One thing I want to add is you might not only want to make it difficult for humans to understand, but also make it difficult for machines to understand. This is in order for to prevent automatic analysis of your code. So I want to add that one. So you might want to use obfuscation if you're talking about malware. Malware is, I guess, one of the most common use cases for obfuscation, because whenever someone wants to spread a virus, they need to make sure an antivirus doesn't detect it. So in general, if you have packers, you have cryptors, you have anything that makes it harder to detect this virus. So I guess this is like the evil use case for obfuscation. But of course there are some other less evil use cases. For example, back when Microsoft Silverlight was a thing, they had a DRM component, which of course you need to obfuscate, as someone can go in, break this component, extract your audio or video stream. Currently you also have something similar. Netflix of course has also a DRM deployed, and you can bet there's also obfuscation involved there, so we can't just like dump the stream out of it. Then of course, if you're talking about license checking and you use like a license key model, you often have the problems that people are writing keygens for your software. And if you make like your key check function obfuscated, it is far harder to write a keygen for it, because you don't really know how it works. And also in the same aspect, it is really hard to patch a software that is obfuscated in order to skip this key check. So you can't like use cracks to bypass a key check. And lastly, if you're talking about the gaming industry and mostly about copy protection, the Nuvo is really, they're rather new, but they've been used for a lot of games, and currently, at least from my view, they are one of the most advanced ones. And they can be used both for game copy protection, so people actually need to buy your game, and they're also currently branching out into anti-cheat protection, so they apply further obfuscation to prevent people from writing like hacks and stuff like that, because usually you also need to reverse the game to influence the game. So now I'm going to quickly show you how you could potentially go ahead about reverse engineering a target you want to know what is actually going on. So of course, this is going to be a target I know a bit, because I can't go here with a completely unknown binary. And essentially, this is what you'll see once you load it into Jidra. And you start with a disassembly, and it just dumps you on the entry point defined by the architecture. So, okay, we know it's a Cortex M. So the second entry is in the interrupt table is probably going to be the reset handler. So let's go to it. And as you can already see on the right, there's a rather small C code, which we can increase. And this is essentially one of the strengths of Jydra. It gives you C-like decompilation for anything you throw at it. And in this case, we have like the usual while loop, probably used to initialize ports of the RAM. Here you have another while loop, and this time it is initializing with 0. So we are most likely talking about the BSS sections that contain 0 initialized variables. And then you have in the end some further configuration of some. This is most likely a peripheral because it's in the peripheral space. And then you have 2 function calls. And I'm going to hazard a guess, the last one is probably the call to main. So let's follow it. And again, you just jump to the start of this function, and you can see on the top some variable declarations, and Jydra is trying to guess what types they are. And if you scroll down a bit, you see a whole lot of function calls. Again, this looks like a peripheral address. A lot more function calls, but at some point you start seeing loop constructs. And this is something you see in a lot of embedded applications that are essentially running some kind of endless loop that is doing like reading from peripherals, some data processing, and writing to other peripherals. So let's see what's going on here. This looks like some kind of calculation, but what is it actually calculating? I don't know yet, but let's see what goes into this calculation. You have one variable. If you just see, okay, let's highlight where it is set. Okay, this is set to some static value we don't actually know. So let's follow the other variable that is used. It's this one. So as you can see, it is not set anywhere on top, but on the bottom it is set to 0. So this seems kind of weird. So let's see where else in the program it is used. So we jump to the really small disassembly view. Which you can also increase. And this lists all the references to this variable. And you have, of course, the references. This is actually not the one I was looking for. So you have the references inside you have 2 references in the same function. This one, this is exactly the function we just came from. So let's look at the other reference that is right actually. And you end up in another function. And function starts here because you have your traditional ARM Cortex stack allocation with your push. And again, if you look at the disassembly, you can see, hey, our function is our variable is assigned the result of this function call. So, and please note, this is like a peripheral region address. And if you go inside this function, oh, okay, this is just some kind of wrapper, most likely provided by the API to allow you to read a peripheral. So let's go out, and now if you look it up, you can like add these 2 addresses together, look in the memory map, look in the manual, and you'll find out what this is. And I'm going to spare you looking it up yourself. This reads the actual the current timer value from timer 0, which kind of makes sense if you follow it back to where we came from, which is this calculation. And once you start like transforming it in a bit more readable C code, and for example, you convert the hexadecimal values to decimal values, and you're going to notice, hey, this calculates the distance that is displayed on this little display here from the time of flight of this ultrasonic sensor. And usually what you have here is not like this simple calculation with lots of fixed constants. You usually have something like that takes into consideration the humidity, the temperature, and all that things. And usually have a really big algorithm that you might want to be able to protect because you put a lot of effort into building this model. So I just showed you how you do it statically. but you can also do it dynamically if you don't have like all the references to this variable. So let's just copy this address and move over to our trusty debugger. So let's attach it, and if you could see, currently the distance is no longer updated because I just halted the microcontroller. And now I'm going to set a watch point. And continuing, and of course GDB crashes, which is not intended. And this time, this is actually the binary with symbols because I want to make it a bit easier for myself. The problem is you sometimes get your breakpoints not exactly at the location you wanted to break. So if we scroll up a bit, you can see, okay, this is the instruction that triggered the breakpoint. So we need to look in R9, and R9 contains exactly this address we are looking for. And now we're on the main function, which is exactly the place we were before. But now we know, okay, this is where it's read. So let's check where it's updated. And again, this time you see the symbols, and we are breaking the external interrupt handler. And if you look it up, this one can be triggered by the timer. And again, let's go 2 instructions back. So R2 should hold our address, and yeah, this is like how you use a dynamic analysis method, rather manual dynamic analysis method, to learn more about your program. And this is just what you might want to prevent using obfuscation. You can, for example, try to make my life harder if you obfuscate in a way that prevents me from you looking at it statically. But you also might want to deploy some anti-debug methods. So I can't do this, because this allows me to rather quickly look through the data flow and try to reason about your program. So just further demonstration what usually goes on if you have a binary. You try to locate the entry point because it allows you to gather roughly what is going on. And most importantly, you can look at how the peripherals are initialized. Then you locate input-output. For example, these GPyro write bit functions, because then you can like look for the references, which you can see on the right, and see every part in the code that actually writes to the outside world. Then you can look at what components are there, how are they linked together. And of course, you usually don't get these symbol names, but once you have gotten through a binary a bit more, you probably are adding in your own names. For example, okay, first function, probably your reset handler, then you have a main function, and then you go through and look at the other functions. So you just get a rough idea what is going on. And then you look for something I'm going to call interesting code. This is not something you can define for all binaries. This is mostly about, okay, I'm looking for some kind of calculation algorithm, so let's look for some messy C code. And it's just, okay, this looks like a calculation, let's analyze it further. And what you're mostly looking for is this kind of valuable information. You're looking for something we call features. These are read-write memory addresses in like the peripheral region, and you're also looking for well-known constants. For example, one of these constants we looked at before just happens to be the speed of sound. And of course, if you're doing time-of-flight calculation, you probably need the speed of sound. But well-known constants can also be something like AES boxes or hash initialization vectors. And you're also looking for data processing. For example, if you have a stream of something like a lot of XORs, this is most likely cryptographic code. And then you can gather, okay, this is more probably this kind of algorithm, so you can continue on from there. But then you're also looking for something called connections. And this is how these features interact with each other. The most straightforward one is the control flow information. You have some location which does something that looks like AES. So you're looking at the reference to this code, and you're finding code that calls AES and probably is doing something with encryption or decryption, and you can further follow it to get the key. But you're also looking at data flow information. This is how different parts of the program like communicate with each other. And this is exactly what I did with the debugger. I knew, okay, this memory location holds something important for me, I'm going to look at it. And how can you go about analyzing it? And first of all, the manual way I just demonstrated, and you can also do it with some automated tools, either by scripting it or using some really strong frameworks. And you can also go about it using static methods, which was the first version I showed you. You just look at the binary, you don't actually run it. And the second part is, of course, you just flash it on a device or you execute it in an emulator to just see what it is actually doing. So the first thing, static manual, of course, good old IDA, and anyone who has done any reverse engineering probably has at some point used IDA, but currently JIDA is really catching up. I mean, in some aspects it's better, in some aspects it's a slight bit worse. It comes down to preference. But these are like the standard tools if you're looking to do some static analysis. If you're doing dynamic analysis, in a manual way, you're mostly looking at debuggers, and in my case it would be GDB, because GDB supports this target nicely. But now we are coming to something, at least for me personally, a bit more interesting, which is the automated analysis. And you have frameworks like BEP, the binary analysis platform, or JackStep. And these tools are there to extract like information from the binary in a structured way. Then you have Radaro 2, which again is a framework to do this. And funnily enough, of course, you can also use these two tools, IDA and JIDA. They have a huge scripting capability, and this is what always helps me if I'm looking at a really big binary. And you can just go ahead, write a JIDA script or an IDA script that does something automatically for you. For example, what I did for one binary, there was some kind of dynamic linking going on. So on boot up, some addresses were resolved to function pointers, and these were placed at certain locations so callbacks would work. And I figured it out for one function pointer, figured out for a section function pointer, and then I looked at how big this table was. And we were talking about 150 function pointers, so I was not going to do that manually. So you just hack together like 20 lines of JavaScript, let it run, and it's going to annotate all the call size with the correct function. And that's a really strong advantage of these tools. They give you like your automated analysis combined with a really good manual analysis. And on the like automated dynamic approach, you have something like wall grind, which you can use to look at how your application is executing, and you can instrument it while it's executing. And for example, you can use it on x86. Probably a lot of you are using it for memory leak detection or memory error detection, but you can also use it on like ARM targets, of course not embedded targets, but desktop targets. And you can also use QEMU or, for example, Unicorn, the bits on top of it, and this one can emulate small devices. So obfuscation methods. First of all, let's look at it from like the academic side, and there are a lot. And you can classify them into different things, and we are not going to cover all of them. There's just not enough time. So first of all, we are going to look at something called data obfuscation. Data obfuscation essentially has a target. You want to make it hard for an attacker to interpret the data that is in your program. And just an example, some really basic thing is array transformation. Instead of having like an array with 10 ints and you access like the 6th element, you just say, okay, let's use a multidimensional array. And in essence, this is doing exactly the same, but it looks slightly different, at least on the C level. Whether your compiler actually translates it to different instructions is another thing, but yeah. And also you can use like true arrays, so you need to kind of check, okay, in which range is my index, and use that one to access it. This is like a really basic transformation, and usually even basic tools can circumvent it because there's not much changed actually on the binary side. But something that is a bit more effective is using one-way transformation. For example, in this case, you just want to check a variable for a certain value and want to do something if this happens to be a certain value. In this case, it's just your usual dead beef, but for example, if this were something like an AS key or a certain value read from peripheral, this would tell me a lot about what you're actually trying to achieve and what is going to happen. So what you can do instead is you use a one-way function like an MD5 sum. You calculate the MD5 sum of the value you want to check against, And on runtime, you calculate the MD5 value of the value you want to compare. And in the end, you can just say, okay, the MD5s match, so my value probably also matched. And this way, to know, okay, you actually checked against that beef, I would now either need to invert MD5, which happens to be hard, or I would need to brute force all 4-byte values to check what you actually meant. Of course, this can be done with 4-byte values, not so difficult, but once you're talking about like input from an outside source, it can be like 10 or 20 bytes. Then you're getting into ranges where this is not practical anymore. And you can't easily like remove this kind of obfuscation. But of course, you can also try to obfuscate your code. And the first one is also rather simple. You use instruction substitution. So instead of, okay, I'm just going to call the function through, let's do what BL does actually internally, manually. You move to the linked register, the next instruction, and you just branch to foo. It does exactly the same, but of course you use a pattern that might not be recognized as a core. And you can also do this for arithmetic instructions. Instead of using add, yeah, you negate R1, subtract it from R0, and whoops, of course the result is again going to be equal. And yes, these transformations are fairly simple, but you can get more complex, for example, using mixed Boolean arithmetic, which can expand like a simple add to a really long expression that needs to be simplified by, for example, a statement solver. And another thing is you flatten the control flow. This essentially means is you turn it in a big switch case. So instead of having like one basic block that has a conditional branch to another basic block or follows a different path, all of your basic blocks are always targeting the same basic block, and you're using like a register or a variable to tell which basic block should be executed next. So in essence, this is what your control flow graph is going to look like, and as you see, everything is on the same level. That's why it's called control flow flattening. This you can also often automatically remove by just looking at how the dispatcher works, what is the value that indicates the next basic block, and just yeah, essentially reorder the control flow. So now we leave the academic side and look at what you can actually do in practice and what is actually done in practice. And first of all, we're going to start on the desktop. And a desktop is somewhat different than like your embedded systems because you essentially only execute from RAM. Anything you want to execute is first loaded into RAM and then fetched by the CPU. And this brings some implications with it, which we are going to see later. And we are talking about a really very high performance desktop system. And yeah, you just have a lot of computation power to do anything. And you have high parallelism. Nowadays, like a dual core is your standard, quad core is more like the norm currently, and you're going to like multiple cores, so you have a lot of power in parallel if you can use it for your obfuscation. And you have a really large amount of RAM, like 4 GB happens to be quite small nowadays, and we're talking about like 32 GB of RAM. And you have a really huge amount of storage. So if your obfuscation happens to be really big once it is addressed, like on your HDD in your file system, you don't actually care if it takes like 1 GB for your binary, because there's enough space for it. So one approach is called code packing. If you imagine like your traditional binary, you have on the top like a header, which is either going to be your ELF header or your PE header, and then followed in the simplest case by a text section, which holds your code, and by the data section, which holds your writable data. And the packer is going to go ahead, insert a small stub of itself that can unpack it at runtime, and transform your code into something, yeah, usually a bit smaller. For example, you can pack with zip or with UPX. Doesn't really matter. It's just some kind of scrambling of your text section. And this is what is actually going to lie on your HDD, just some text, a small text section with a bootstrap code and your packed data. And once you start executing, the execution will actually start inside the unpacking routine. And this is going to restore your original content to your RAM, and of course going to jump in there. And at this point, execution continues as normal as you would expect. This is rather easily defeated because, yeah, you can just dump out the original text section once it's unpacked and be done with it. And so even on the desktop side, for the common packers, there are tools that do this automatically. Code encryption, really similar. You again start with your binary, but this time you encrypt it with a stub, and you decrypt it at one time. So I'm not going to go through it in detail. It's the same, but this is the basic approach of encryption. You can also do something like this. You still have your stub, but you have multiple parts of the program, and they are not at all going to be decrypted at the same time. So again, you start in your small stub. It's going to decrypt some part of your binary. You jump in there. Once you're finished executing, jump back, and then you either remove it from RAM or encrypt it again, depending on how you want it. And then you execute the next section, and so on. Of course, you can also circumvent it, because you can just like watch for writes into this encrypted section and dump out the original. You can just modify the stub, but this is like a little bit harder. And something that is, I guess, the most commonly used in packers like vmprotect or Termiter is virtualization. Virtualization not in the sense of like VMware, but you emulate a smaller, sometimes smaller CPU inside your actual CPU. So you have your real big like CPU, and then you just simulate another one. But this is not fun. So let's stack it together, and at some point, someone is really going to lose track at how many layers you're inside, and also you can influence like the state from the innermost layer to the outermost layer, change the decoding and all that stuff. And the most important thing is you can really influence what your instruction set is going to look like of all the layers. They can all be different, they can all be the same, and you don't need to like implement an add code. You can an add opcode. You can implement like an add and multiply opcode. So you need to like have some side effects you later need to reverse. And another part is don't try to read it all. This is like an opcode handler of a commercial protection tool, and all of this essentially adds to memory locations and writes it to a register. And this is the point where someone in this tool is just going to give up, because in order to identify, hey, this implements the add semantic, you need to follow everything through memory accesses, and it's usually not computationable. But Tim and Moritz actually wrote a tool that can tell you, yeah, this looks like an add. And I can really recommend that talk. So what are the problems? With code packing and encryption, as I already said, you can easily circumvent it, but apart from that, you also have some resource constraints that will break it on embedded systems. You have a whole lot of RAM usage. For example, if you're talking a device with like a few hundred kilobytes of RAM, but 2 megabytes of flash, you can't fit your whole image into RAM to decrypt it before execution. The decryption function itself, if it's cryptographically secure, it might be too slow for your device. But there's also a potential advantage. If you use the right packer, it might actually reduce the size of your code. And if you have some RAM to spare, it might be advantageous to just store it packed in ROM and descramble it on runtime. And if you look at virtualization, we are going to talk about it further, but the further you nest your VMs, the longer a single execution will take. And we are going to look at it in a second and handle complexity. If you're using like 100, 200 instructions to implement a single virtual instruction, it just doesn't scale from a performance point of view on small devices. So let's look at what you can do on embedded devices. So control flow flattening, if you remember, you just make everything flat. This is easily done on embedded applications. So you start with your really simple function. It just does something, just adds stuff together. But as you can see, it has actually 4 basic blocks that are linked with jumps. And this is easily disassembled with control flow graph from. So you want to flatten it. So you place every branch with a branch to a dispatcher, and you use some register to tell the dispatcher where it should actually go. And the dispatcher, in this case, also relatively simple. You just look at the index and read the target from your jump table and jump to it. That's everything. And again, this is easily breakable. you can easily write like a JITOR script that detects, okay, this branches to the dispatcher, stores the index, and then, for example, just replaces the branch to the dispatcher with a branch to the right instruction. Another approach would be, if you use the same function, you want to virtualize all branches. Just rely on a memory area instead of a direct branch. So you again just replace all the branches. This time we can do it in place. We don't need to go all the time through a dispatcher. And again, this is your jump table, fairly simple. And of course, if you place your jump table in ROM, this can also be broken with static analysis. But the most important point is, if you somehow manage to prevent an attacker from knowing this jump table, they don't actually know how to get around in your code. And what you can, for example, do is computate it at runtime. So an attacker needs to open like your currently running device. Of course, you need to secure your calculation, else it is easily undone. And now we can look at virtualization. Of course, on embedded devices, we can't use like this whole mess of a lot of instructions. So our add dispatcher is going to look a little bit simpler. This is about what you can do on embedded devices. You just implement it with some kind of accumulator, a machine, and then you just do the rest of the decoding. So again, we start with like your CPU, your small microcontroller, and let's say you can get around about 160 million instructions out of it per second. If you want to prioritize an image of it, this is essentially what you can do on one of these things with your standard Cortex M4. 160 million, you round a lot, you leave a lot of it out, but we're just going to some calculations on it. So 160 million per second, kind of hard to imagine it. So let's say you need to accomplish a single task in like 1/10 of a second. So you have a budget of 16 million instructions. Sounds a lot, and you can get a lot of it done. But now, of course, we move one layer into the virtualization machine. So let's say you have a really small virtual machine, and it requires 20 native instructions to implement one virtualized instruction. So, of course, instead of 60 million instructions, you suddenly only have 800,000, which, of course, is still a lot. You can get quite a lot done. But now, of course, we want to go deeper. So we add another layer. Again, let's assume, okay, you need 20 virtualized instructions on the first layer to implement the next layer. So suddenly you only have 40,000 instructions. Still, that's okay-ish, but it starts to get a bit uncomfortable. But if you move even further down, at some point you have like 5 instructions you can execute. And at this point, it's just not practical anymore to use this. So this is one aspect. You can't nest really deeply on embedded devices because your performance is going to suffer greatly. So let's look at the other dimension. Let's again, we have a budget of 60 million instructions, but this time we want to use this kind of dispatcher. So I'm just going to assume these are like 100 instructions, and so your first virtualized layer, you can execute 160,000 instructions. Yeah, it's okay, you can work with it, but second layer, and suddenly you have only 1,600 instructions. This is already nearly impractical. And of course, if you go deeper even further, at some point you start needing a decimal point, and you won't get anything done. And this is like the biggest problem on embedded devices. You just don't have the performance to implement something like that. But what you can do is, you can do a trade-off like, okay, I'm only going to nest like to level 2, which is going to reduce the security a little bit, and at the same time I can maybe use like 30 instructions in my dispatcher to kind of obfuscate a bit that it's an add. So it's always a trade-off, and this is like a core aspect of embedded obfuscation. You have really a lot of possibilities, but you require different approaches. Of course, you can just try to throw de novo on your ARM Cortex M4. It's not going to work. And you need really specialized solutions. And well, I got that point. Actually, there's a lot of like trade-offs. You can scale on multiple axes. You need to find what is your threat model, and it's just not that easy. So this brings me to the Q&A part, and if there's anything you want to answer, feel free to go ahead. Sure.
So from your experience, how long does it take to do your very first obfuscation from working code to actually have something that cannot be reverse engineered that easily?
It really depends. First question is, of course, like, are you talking about like fully automated obfuscation on like software you haven't seen before, for example, which is a model of these packers for malware, and these need to work with like every code you can throw at it, and this is going to require a lot of effort, and you're probably limited in what you can do. If on the other hand you're talking about obfuscating just your own program and you want to do it once, then at that point you just go ahead and you look at the disassembly code. Oh, I can go in here, modify it. I can go in here and do this. Or for example, you can say this port is not performance critical. I can protect it really well. So I guess the answer is it highly depends, as always. And writing like your first packer, which is the most simple thing, probably like a few days to maybe a week if you already know the environment. But writing something that can rival like commercial solutions is, you're talking about multiple people spending months to years on it, because you're mostly spending time on like understanding the software, because you don't want to break anything with your edits. You spend a lot of time on analyzing what might be the performance critical parts of the software, and you're also spending a lot of time dealing like with integration into the toolchain of the developers. Because, for example, you want like some kind of annotation system. Someone wants to tell you, hey, this code is really performance critical, don't touch it. Or here, we spent 2 years trying to understand this calculation, please protect it really well. And then you need to just think about what kind of compiler are they using, what kind of linker are they using, can we actually modify their code, or do we need it with like an external annotation file? So yeah. The actual implementation can be quite fast, but then you're talking about compatibility issues, which is always a big pain. Further questions? Sure.
Well, you talked about a virtual machine inside my program, and I can imagine that you don't want the same instruction set. What kind of tooling do you use to write software for targeting that virtual machine?
Yeah. If you're talking about something you only yourself write, you usually just write your small assembler, usually in a scripting language, that just does your opcode selection and emits a bytecode. But of course, if you want to do it for a lot of people, you can try adding an own backend for it to LVM. But usually you just end up with something like how's it called? A transpiler. You take an existing, for example, bytecode language, and you just translate their bytecode into your bytecode. Or you take x86 instructions and you have like a mapping of, okay, this is an add I implemented using these opcodes in my virtual machine. And for example, commercial protection tools, they can generate multiple different kinds of VMs and virtual machines for a single binary, and yeah, essentially you need to do transpilation for that. Sure.
So I mean, obviously this doesn't make reverse engineering impossible. It just slows it down, correctly? Yeah. So is there any possibility to, or is there any measure to know how much it slows down the speed of reverse engineering? Because I mean, if it just makes it, I don't know, 5 to 10 minutes longer using an automatic tool to do that. And how much is it worth it? And how much does it cost?
Yeah, I mean, this is also a problem we are facing, because in the academia, if you look at academia, obfuscation is already broken, because you only need like some effort to break it, because it's not like crypto where you need to brute force like 2 to the power of 64 number of bits in a key. It's just, okay, yeah, you just sit someone in front of it and he's going to solve it. So academically it's broken. But in practice, you don't actually care if it's broken. In theory, you're talking about how much would it cost an attacker to analyze it. And this part is really, really hard to answer, because, of course, it matters who is looking at it. If it is someone who is really, really experienced in this field, who knows gyro scripting, who knows how to use a debugger, it's going to be a lot faster than someone who just started doing it. But at the same time, if you use like an expert and tell it, here, this is this is like an obfuscated binary, we want to know how it works, and you give him just this binary, it's going to take him a lot of time, and because he's an expert, you're going to pay a lot of money. And at this point, the security is some kind only expressed in like economic terms. How much money would it cost to reverse engineer it compared to your traditional one? And we really don't have a metric for that one. There are efforts in place that are trying to find like an academic metric, which later you might be able to translate it into an economic metric, but it is far too early to have like a metric for that. So in general, we can just say it makes it harder. And of course, you can, inside your company, you can have like your red team that are doing nothing else than breaking your obfuscation, showing you how they did it, and then you develop methods to make it harder. And if you, for example, take someone who is experienced in it and it takes him 1 month, you can say, okay, you probably gain 1 month, but of course, if he just didn't like get your obfuscation method that fast, it could be that it was 1 month and it takes someone else like a week. This is always hard. But if you want like a reference point, Denuvo is used to protect like AAA game releases, and they are talking about like 2 weeks of protection. But this 2 weeks is spent by groups of a lot of people, really talented people trying to break your game, and it takes them 2 weeks. So this is kind of like the protection you can expect, like 2 weeks of 10, 100 people looking at it, but really depends.
You've been comparing it with let's say system level obfuscation techniques like Denuvo, but also there are anti-debugging techniques that are being improved and evolved. I can imagine that on the embedded there are more chances of maybe doing some sort of anti-debugging. Is that in scope for you?
Yeah, of course, it's of interest to us, but if you're talking about like your desktop system, like for example Windows, you have a fixed system, and it also gives you a lot of possibilities to like detect something is going on. Like you can try to profile there's a hypervisor running, and then at some point someone has full access to a RAM because they control the hypervisor. Or, for example, you can use something tricky like nanomites, so you have 2 processes that debug each other and have race conditions inside, and if you break one of them, the other one is going to crash. And on embedded, you can't really do that, because on embedded, you're limited to, like, usually a single thread of execution. And you might be able to try to construct race conditions using DMA or something like external interrupts or your timers, but it's really hard. So another problem on embedded devices is it is really easy to emulate your complete chip. You can't really emulate perfectly an x86 CPU. There's just too much going on. You need to make it perfect if you really want a perfect prevention of detection. For example, you need to emulate all the cache hierarchies. You need to emulate, if you really want to go that far, the whole speculative execution engine, so someone can't use timing to figure out, hey, I'm running in a virtual machine. On embedded, it's really easy because the pipelines are small. They are, for some architectures, usually not the current ones, they are cycle-accurate emulators, which are essentially used in retro gaming because these need to be cycle-accurate. And if you invest enough time, you can also get quite close to like an actual ARM core in an emulator. And at this point, someone controls everything that is fed to you, including like how often your clock is going to tick. And at some point, it's just really impossible to defend against it. So yeah, you have a lot of possibilities because you control the entire system and you can connect to like the outside world. But at the same time, you have the danger that someone's controlling your outside world.